Hello, my name is Michal Edelstein, and I will present the first part of our work, PH-CPF, planar hexagonal meshing using coordinate power fields. This is a joint work with Casper Pluta, Amir Waxman, and Mirela Ben-Chen. Casper will present the second half. Given a surface represented as a triangle mesh, our goal is to compute as output a planar quad or hexagonal mesh. Tools for planar quad meshing exist, but hexagonal remeshing poses additional challenges. First, depending on the curvature, we need different shapes of hexes, both convex and non-convex ones. Also, for the hexes to be planarizable, alignment and anisotropy are highly constrained, leading to difficult optimization problems. Therefore, existing standard remeshing pipelines, which are applicable for planar quad meshing, do not generalize to planar hexagonal meshing. We thus introduced a new general framework, which is flexible enough to handle planar hexagonal meshes and is also applicable to other problems. To compute the output mesh, we introduce coordinate power fields, CPFs, which are a pair of tangent vector fields on the surface that fulfill a certain continuity constraint. We proved that the fulfillment of this constraint guarantees the existence of a seamless parameterization with quantized rotational jumps, which we then use to regularly remesh the surface. One popular application is for architecture, for example, building a structure from hexagonal wood panels. Our framework is as follows. We start from an input surface. We build a parameterization to the plane, and then we take a grid on the plane and map it to the surface using the parameterization. This gives us the output mesh. To generate a hexagonal mesh, we use a triangular grid that has 3 directions in the parameterization space. We again take a grid on the plane, its dual is a hexagonal grid, and mapping it to the surface using the parameterization will give us the output hexagonal mesh. Mathematically, we define the parameterization in the opposite direction. So, given a planar domain U, we map it using a parameterization R to a surface domain omega. Given the vertices and the faces of the 2D grid, we take the images of the vertices on the surface as the new vertices, and the same faces, and get a quad mesh on the surface. Now consider the derivatives of R. The derivative with respect to U is a tangent vector field on the surface, denoted by capital U, which is parallel to the iso V lines, and similarly for V. These vector fields are called coordinate vector fields of R, and they prescribe the directions of the edges. So controlling them will give us control on the resulting quad mesh. Starting from an input shape, we prescribe 2 vector fields UV, and then find the parameterization R such that UV are its derivatives, and then continue as before. So we define different constraints on UV according to our requirements, this is our input, and get the shapes as output. But first we need to ask whether there exists a parameterization R such that UV are its derivatives. This concept is called the integrability of UV, and is the main technical challenge in this approach, how to optimize for UV such that R exists. To define the integrability, we first talk about a gridable parameterization, which allows for seamless cuts. Assuming we have 2 different parameterizations, mapping 2 planar domains to 2 surface domains, we get a gridable parameterization when the composition of going to the surface and going back is a grid automorphism. So rotations by integer multiple of pi over 2 and integer translations. In the discrete case, we look at each parameterization as the mapping of each triangle. Vector fields are piecewise constant per face and represented in an arbitrary local basis per face. The partial derivatives UV are by definition the push forward of the axis under the parameterization. Using the local basis, we create a 2x2 matrix whose columns are UV. This matrix is invertible when U and V are linearly independent, and it's easy to show that its inverse defines the parameterization up to translations. Discrete integrability means that if we zoom in on our surface and consider 2 adjacent triangles, they each have their own map R to the plane, which we denote by Rj and Ri. Now, consider the common edge Eij. These 2 maps are integrable if they agree on the pre-image of the edge. Since we only need gridable integrability, it's enough that the maps agree up to rotations by 2 pi over n, where n is the grid we are using, so 4 for quads, 6 for hexes, and so on. For our integrability, we also need linear independence of u and v at each point. We denote such vector fields as LICO, linearly independent and consistently oriented. It is required to guarantee bijectivity. Furthermore, by combining the integrability with the relation between the parameterization and uv, and representing 2D vectors using complex numbers, we get the following constraint, to which we add the LICO constraint. If two vector fields uv have this property for any interior edge, we call them coordinate power fields. CPFs guarantee the existence of a corresponding, seamless, rotationally quantized global parameterization. If these constraints hold exactly, then we can find the parameterization. The proof is given in the paper. The only thing that is not handled here are the integer translations, which are a subset of grid automorphism, and are solved after integration using a greedy approach that guarantees bijectivities. Now that we have this condition, we combine it with other constraints and find a parameterization. But first, we discuss the differences between our approach and previous methods for vector field-based remeshing. There is a large body of work on global parameterization, meshing, and directional field design. Some methods compute crossfield first and only then a parameterization. This means that the sizing is only addressed in the second step and cannot influence the singularities. The integrability is also only enforced in the second step, resulting in parameterizations that can be far from the input crossfield. Finally, using a crossfield implies that the resulting gradient directions are orthogonal, which is not always preferable. Our method addresses all the components except integer transitions, meaning integrability, sizing, and alignment, in the vector field optimization stage. Other methods allow for non-orthogonal, non-unit length fields in the first step. However, they do not guarantee integrability, and again, the resulting parameterizations can be far from the input fields. IPV, CPV, and DIFF are the only methods that allow for non-orthogonal fields and optimize integrability. However, IPV defines the integrability condition on the surface and not on the parameterization domain, representing a bigger space than that of coordinate vector fields for some parameterization. In CPV, integrability is defined through the discretization of the Lie bracket, which in general does not guarantee discrete integrability. Also, both CPV and DIFF are tailored to Chebyshev nets and not necessarily extendable. Looking at the differences between the formulations, crossfields are represented by the nth order roots of a complex number per face on the surface. They are unit length and orthogonal, forcing the 3D quads to be squares, which limits the solution space. Polyvectors are represented as the roots of a complex polynomial per face. They do not require rotational symmetry, allowing for non-orthogonal, non-unit length fields. However, they allow for any set of consistently oriented vector fields, forming a much bigger space than that of CPFs of parameterizations. CPFs formulate the pullback maps as the nth order root of a complex number on the plane, thus allowing for non-orthogonal, non-unit length fields and enforcing discrete integrability, representing the space of gridable parameterizations. This table summarizes the property of different methods. Our method is the only one that allows for anisotropics and skewable quads, guarantees integrability, and therefore has the exact amount of degrees of freedoms as needed. We show a few results for planar quad meshing using and their comparison with the polyvector methods by Diamanti et al. The color represents the planarity of the faces. We note that we applied the same planarization post-processing as for our approach. We also show the number of faces and the Hausdorff distance to the source mesh for each mesh. Notice that we got a better Hausdorff distance using a smaller number of elements and that we have less artifacts. We have additional results in the paper. Back to our formulation, we can add a variety of constraints to the CPF and LICO constraint. Alignment allows to align quads or hexes to given directions. We also add smoothness, constraint on the metric, and orthogonality. So given a set of constraints, we compute UV that lead to a matching parameterization. Here we show the results for quad meshing from a random initialization, meaning U is random and V is rotated by pi over 2. And we see on top the initial flow lines of UV for a few meshes. The final ones appear below. And these are the resulting meshes without planarization. And you can see that even though this is a non-convex optimization scheme with a random initialization, we still got good results. Now Casper will explain about planar hex meshing.
Thank you, Michal, for providing the first part of the presentation. In the second part of our talk, we will focus on an application of the CPF framework for computing planar hexagonal remeshing. As mentioned, hexagonal remeshing poses difficult challenges. First, depending on the curvature, we may need non-convex hexagonal shapes. Additionally, for the hexagons to be planarizable, alignment and anisotropy are highly constrained, leading to difficult optimization problems. Therefore, since existing standard remeshing pipelines do not generalize to planar hexagonal meshing, we use the CPF framework for this problem. Before we explain our constraints for the CPF framework, let us first discuss some related work. There exist methods aimed at generating non-planar hexagonal meshes. Here we focus on planar hexagonal meshing. Some of the earlier methods use the duality with triangular meshes, but they often do not lead to regular planar hexagonal shapes. Other approaches use Dupin indicatrix by scaling to construct a hexagonal mesh. However, they require a special treatment for singularities or manual adjustments in certain regions. Let's then talk about the constraints we need to formulate in the CPF framework in the context of hexagonal meshing. The first aspect we need to consider is the alignment of the hexagons. In the elliptic regions, we have a lot of freedom, and in fact the alignment is not necessary for planarity. Nevertheless, we align in these regions with the principal curvature directions, as this leads to more regular hexagons. Here the elements are convex and have 6-fold rotational symmetry. In the parabolic regions, we need to align the hexagons with the ruling direction, meaning the minimum absolute curvature direction. Further, the hexagons have brick shapes and only 2-fold symmetry. Finally, in the hyperbolic regions, we can align with either minimum or maximum curvature directions, but still the elements have 2-fold symmetry. To see the importance of the alignment, consider the following example. Here we compare the result without and with the alignment constraints. The colors here correspond to planarity error measured per phase. Note that without the alignment we still get planar hexagons, but the PH mesh does not approximate where the input surface. Another aspect we need to consider is the anisotropy of the elements. We can obtain the expected shapes of the elements by considering the following thought experiment. Let's cut the surface with a plane parallel to the tangent plane. We will obtain different shapes depending if it is an elliptic, a parabolic, or a hyperbolic region. These shapes directly map to the shapes of the hexagonal elements. The shape we obtain is a uniform scale of the Dupin indicatrix. This is a conic curve which has different types, such as an ellipse, 2 parallel lines, and 2 conjugate hyperbolas, depending on the curvature. Its expression is given in terms of the principal curvature values and directions. Thus, our goal is to define the element anisotropy using a regularized Dupin indicatrix, which is a convex conic with the same aspect ratio as the Dupin indicatrix. Our third constraint relates directly to planarity. As in planar quad meshing, we require that the main directions of the hexagonal element are conjugate. In the parabolic regions, though, any direction is conjugate to the ruling direction. Thus, we can get planar hexagons which lack bilateral symmetry. Thus, we enforce an additional orthogonality constraint leading to better shaped elements. This concludes all our constraints, which we then use for CPF. We first set up CPF with n equals 6 to compute a regular triangular mesh. We add constraints for alignment, where we use a 2-rosy guiding field as the alignment field. Scaling using the regularized Dupin anisotropy and conjugation orthogonality. We refer you to the paper for detailed construction of the guiding field and the Dupin scaling, as well as for the other practical implementation details. Our final pipeline is as follows. We take the input mesh, compute the constraints, feed it to CPF to generate a semi-regular triangular mesh with the correct alignment and anisotropy. We show here the constraints we computed using the guiding field, overlaid on the output mesh. So it is clear that the triangular edges follow the input direction. Then we dualize this mesh, leading to a semi-regular hexagonal mesh with convex faces. Finally, we planarize this mesh using a standard planarization method, leading to our final PH mesh. We can then compute a phase offset mesh for various purposes. Now, let us show some results. Our method has two intuitive physical parameters which allow us to control the mesh resolution. For example, here we started from a torus and varied the parameters to get a variety of planar hexagonal meshes. The upper rows show the dual meshes, and the lower rows show them after planarization. Note the different scale of the planarity value in the top and the bottom rows. This parameter allows us to control the Hausdorff distance from the input mesh, shown in the orange plot, at the expense of using more faces shown in the blue plot. We compare our results to the method of Lee and colleagues. Note that we obtain better planarity and smoother flow of the faces, especially between regions of different curvature. Furthermore, our algorithm is robust and can handle a wide variety of general and difficult meshes, even those with large curvature variation, such as bunnies and other interesting shapes. We also obtain good resolution on a variety of architectural meshes. As a proof of concept, we built a model from a construction paper. In order to do so, we printed 2D faces together with connectors, and then we cut them and assembled the mesh by hand. In the near future, we plan to do another fabrication in using a laser cutter. To conclude, we propose a new framework for parameterization-based meshing, denoted by coordinate power fields. We use the proposed framework for designing an algorithm for planar hexagonal meshing. We believe that our CPF framework is general enough to be successfully applied to other geometry processing problems. Thank you for your attention.